in the new lecture of the recurrence relation. So here in the last lecture we discussed about the solution of the recurrence relation by the iteration method. So here we will study about the recurrence solution of the recurrence relation by characteristic root method. So what is the characteristic root method? Here our solution, the complete solution is the homogeneous solution plus particular solution. So we give our solution by homogeneous solution plus particular solution. So first we solve here in this lecture the homogeneous solution. So this is our the recurrence relation in terms of an minus 1, an minus 2, an minus k, and c1, c2, ck are the constant coefficients. So if our fn is 0 here, so we say that this is our the recurrence relation of the homogeneous recurrence relation, and the solution is the homogeneous solution. Now here to find the solution by the characteristic root method, here in this homogeneous recurrence relation we put an is equal to r raised to the power n. So when you put here an r raised to the power n in place of an, so you will get r raised to the power n plus c1 r raised to the power n minus 1 plus c2 r raised to the power n minus 2 plus up to ck r raised to the power n minus k equal to 0. So we get this type of equation. Now after that we have to divide this equation by r raised to the power n minus k, means the lowest term from the lowest term, or you have to divide it. So divided by r raised to the power n minus k. So now we get this equation r raised to the power k. When we divide it r raised to the power n by r raised to the power n minus k, so we get r raised to the power k plus c1 r k power k minus 1, c2 r to the power k minus 2 plus ck, because r raised to the power n minus k it is divided, so it becomes ck is equal to 0. So after doing this process we get this equation, and this equation is called the characteristic equation of the recurrence relation. And the roots of this is r1 r2 to rk, because our equation in kth term, so we have the kth root of this characteristic equation, that is r1 r2 rk. So these are called the characteristic roots. Now our solution is depend on these uh, characteristic roots. Which type of characteristic roots we have, so our solution is depend on that. So first we have, suppose our roots are real and distinct roots, right? So here we have this recurrence relation, and this is our the characteristic equation. After processing a, put an is equal to r raised to the power k, and after divide r raised to the power k minus 2, so we will get this characteristic equation, and these are the roots. So here we discuss about that of our roots are all real and distinct. All are distinct, so our solution is this. The solution of an is an equal to, we have to put our solution b1. If we have the roots are r1 r2 rk, all are different, so we can put our solution in the form of b1 r1 raised to the power n plus b2 r2 raised to the power n plus up to bk rk raised to the power n. So we have this type of solution where b1 b2 bk, what are these? These are the constants, right? And we can find the values of these constants b1 b2 bk by the given initial conditions. Otherwise, if we have not given the initial conditions in our the question, so our solution is up to here. Up to here we get the nth term of the solution of the recurrence relation. And if we have given the initial conditions in the problem, so we can calculate the values of these constants b1 b2 bk from the given initial conditions. Not to worry, actually when you solve the examples and the questions related to this, so you have to clear it. So now let's do the example for this. So here our question is that what's the solution of this recurrence relation? We have given here the recurrence relation is an equal to an minus 1 plus 2 an minus 2. So now we have to solve this. So we solve this by the characteristic root method. So we see that here this solution is the homogeneous recurrence relation. This relation is the homogeneous recurrence relation, that is an minus 1 plus 2an minus 2 equal to 0. So this is our the homogeneous recurrence relation. So what you do here, we have this is the recurrence relation. So first step is that we have to put an is equal to r raised to the power n. So when we put here an is equal to r raised to the power n, so what is our equation? Put here r raised to the power n minus r raised to the power n minus 1 minus 2 r raised to the power n minus 2 equal to 0. Now what you do next step? The next step we have to divide this by r raised to the power n minus 2. So when we divide this by r raised to the power n minus 2, so we get the characteristic equation, and what is that? That is r square minus r minus 2. So this is equal to 0. So this is the characteristic equation of the given recurrence relation. Now, you know how to solve the quadratic equation, because this is the quadratic equation and you know how to solve the quadratic equation. So, solve this quadratic equation, uh, solve this quadratic equation and find the roots. So, when you solve this equation, so we get the roots are 2 and minus 1. So, we have the two roots of this equation, 2 and minus 1. So, now how to write the solution of the recurrence relation if we have these are the distinct, because 2 and minus 1 we have these are the distinct and the real roots are there. So, what's the solution? The solution of an is b1, b2 we have the two constants. So, b1 2 raised to the power n plus b2 minus 1 raised to the power n. So this is the solution of the given recurrence relation. So up to here we have to solve it. But if we have suppose given the initial conditions also, so that is if in the question we have given that a0 equal to 2 and a1 equal to 7, then we now what's the solution of the recurrence relation? So from these initial conditions we find the values of these b1 and b2 constants. So put here we have given a0 equal to 2, so a0 it means that the n is equal to 0 here. So put here n is equal to 0, so you find a0 is equal to b1 2 raised to the power 0, it become 1 plus b2 minus 1 raised to the power 0, it is 1. So we have the equation is b1 plus b2 equal to 2 because a0 is given 2. So this is the first equation. Now next initial condition is given that a1 equal to 7. So it means that we have to put n equal to 1. So it become a1 plus b1 and 2 raised to the power n. So this is 2 minus b2 and plus b2 minus 1 raised to the power 1, so it become minus. So our equation is become 2b1 minus b2 equal to 7. So like that we have the two equations in b1 and b2. So after solving these two equations we get the values of b1 and b2. So we get the constants values b1 and b2. So when you solve these equations you will get b1 is equal to 3 and b2 equal to minus 1. So now we have the values of these constants. So put here in this solution and find the solution in terms of n. So that is an is equal to b1 is our 3 multiply 2 raised to the power n minus what is b2? b2 is your minus 1. So minus 1 raised to the power n. So this is our the solution of the given recurrence relation. Clear? Now you can verify it. You can verify it that your uh, getting the you get the values of a and that is right or wrong. So you can verify it by you put here you have the recurrence relation. So put here because a0 a1 value you have already in the question. So next you find the value of a2 when you put here n equal to 2. So you will get a2 equal to a1 plus 2a0. Right, and you know the value of a1 and a0. So when you put these values of a0 and a1, so you will get a2 equal to 11. Now this is from the given recurrence relation. Now by finding your which solution you find, so here when you put n equal to 2, so you put a2, so 3 raised to the 2 raised to the power 2, it become 4 minus 1 raised to the power 1 minus 1 raised to the power 2, so it become positive 1. So when you calculate it, you will get 11. So you see that both of from the recurrence relation and from your solution, you will get a2 equal to 11, right? So you can say that this is your correct solution of this recurrence relation. Okay. Uh, Next is if our roots are multiple roots are there, means we have the two roots are same or three roots are same and others are different. So what's the solution of that type of recurrence relation? First we have this recurrence relation, and after solving this we get this characteristic equation. In all homogeneous relations we get this type of characteristic equation. So here our roots are, suppose R1, R2, R3. These three roots are equal and others are different. So what's the solution here? How can we write the solution of this recurrence relation? So that recurrence relation solution En here you have to put, because you have the three roots are equal. So you have to write here b1 plus b2n plus b3n square, and because r1 you put here that all roots are equal, three roots are equal, so you put this is r1 raised to the power n, and which roots are different, so you can say that b4 r4n plus b5 r5n plus bk rkn, right? So which roots are equal? So you have, suppose your two roots are equal, so you put b1 plus b2n and r1 raised to the power n. Here we have the three roots are equal, so we put here 1 b1 plus b2n plus b3n square. We use only again here three constant because we have the three roots, but in combination. So this is our the solution, and obviously these are b1 b2 bk, these are the constant, and we can find the values of these constants by the given initial conditions. Okay, so now let's try the example, and then from it's clear from you. So if your question is that your recurrence relation is an equal to 6 an minus 1 minus n an minus 2, and the initial conditions are given that a0 equal to 1 and a1 equal to 6. So now uh, how to solve this? First, this is our the homogeneous recurrence relation, right? So now first step is that you have to put here an is equal to r raised to the power n. So now our equation becomes r raised to the power n minus 6 times of r raised to the power n minus 1 plus 9 r raised to the power n minus 2. So now after that you have to divide this equation by r raised to the power n minus 2, because this is the lowest term. So when you divide it, so you will get the characteristic equation, and your characteristic equation is here r square minus 6r plus 9 equal to 0. Again we get the quadratic equation. So how many roots of this we have the two roots are there. So when you solve this quadratic equation, you find that your roots are 3, means both roots are 3 3 3. You will get the two roots 3 3, so both are equal. So how you find the solution here? So you can write the solution an is equal to b1 plus b2n, right? I told you that if we have the two roots are equal, so we write our solution in the form of b1 plus b2n, and this is one root is there, 3 raised to the power n. So this is our the solution of this recurrence relation. Now initial conditions are given, so by using these initial conditions we can find the values of these two constants b1 and b2. So now put here n equal to 0, because we have given a0 is equal to 1. So when you put here n equal to 0, so you will get a0 equal to b1 3 raised to the power 0, it become 1, and this is 0, so only we have left b1, so b1 is equal to 1. And second one is a1, when you put here n equal to 1, so you will get 3 b1 plus 3 b2 is equal to 6, it is given. So now you have the two equations and two unknowns, so you can find the values of b1 and b2 from here. b1 already we have calculated, that is 1. So now putting here the value of b1 and calculate the b2, so now you have the b2 is 1. So you will get the values of b1 and b2 that both are equal to 1. So now what is our solution? Our solution an is here you have to put the values of b1 and b2 here, so you will get 3 raised to the power n plus n times of 3 raised to the power n, or you can write this in form of 1 plus n 3 raised to the power n. So this is the required solution of the given recurrence relation. Also you can verify it by putting here, you know the values of a0 and a1, it is already given in the problem. So now put here n equal to 2. So from first the recurrence relation, when you put here n equal to 2, so you will get 6a1 minus 9a0, and you know the value of a0 and a1, so it will get 27. And after that, by the solution you can find the value of a2, so that is a, put here n equal to 2, so you will get a2 equal to 3 raised to the power 2 1 plus 2, so it will give 27. So both are equal, so this is verified that our solution is correct solution of the given recurrence relation. It's clear? So okay, so now going on the next roots. If our roots are imaginary roots, imaginary, what's our imaginary roots? Like 2 roots r1 plus minus ir2. So always when we talk about the imaginary number, so we have the combination number plus minus. So now this is our the recurrence relation, and this is our the characteristic equation. So now our roots are, suppose we have the imaginary roots and some are different roots, so r1 plus minus ir2 and others are different. So what's the solution here? So in terms of, if we get the imaginary roots, so our solution is now an is equal to b1 plus, now we have the plus minus, so one time we take the plus and one time we take the minus, so r1 plus ir2 raised to the power n, this is our the first root, and what's the second root? That is r1 minus ir2, this is our the second root. So each and every root we have to include one constant, right? So here first root we can include b1, and for the second root minus we include b2, and these are the different roots, and we know already if we have the different roots, so how to solve this. So main thing is that if we have the imaginary roots, so we can write our solution in this form. Clear? And these are the b1 b2 bk are the constants, and we can find the values of these constants by the given initial conditions. So let's try an example for this. So here we have to solve this recurrence relation, an plus an minus 1 plus an minus 2 is equal to 0. So now let's try this. So this is our the homogeneous recurrence relation. So first step is that we have to put an is equal to r raised to the power n. So it become rn plus rn minus 1 plus rn minus 2 is equal to 0. Now next we have to divide it by r raised to the power n minus 2. So we'll get the again we get the quadratic equation, that is our characteristic equation, r square plus r plus 1 is equal to 0. So now can you solve this quadratic equation? Yes, when you solve this quadratic equation, so you will not get the real numbers. You will find when you solve this quadratic equation, so you will get the imaginary roots. So imaginary roots are minus 1 plus minus root 3i by 2. So here we have the two roots, right? One is minus 1 plus root 3i by 2, and second one is minus 1 minus root 3i by 2. So we get the two roots that are the imaginary roots. So how can we write the solution? So our solution an is, because we have the two roots, so we include two constants b1 and b2. One is for other first root and one is for second root. So our one root is minus 1 plus root 3i upon 2 raised to the power n plus b2 minus 1 minus root 3i by 2 raised to the power n. So like that we have the solution. So this is the solution of our the recurrence relation. Clear? If we have the imaginary roots, so how can we write our solution? And for others, if we have some more, suppose we have the cubic equation and one root is different, so we can write here b3 r 2 or any other root power raised to the power n. Clear? Okay, so last and the point is, if our imaginary roots are repeated twice, right? Our imaginary roots are like that, r1 plus minus I r2, but if it's repeated, so how can we write the solution of the recurrence relation? So here this is our the recurrence relation, and these are our the characteristic equation, and the imaginary roots here r1 plus minus ir2 are repeated twice. So how can we write the solution? So our solution an is here, because in the case of repeated roots we already see in the second theorem that if we have the repeated roots, so we write our solution like if 2 times is repeated, so we write that b1 plus b2, and if 3 times are repeated, so we write b1 plus b2 and plus b3 n square. So here we have the 2 roots are repeated only, so we take here b1 plus b2 n for the first root, r1 plus ir2 raised to the power n, and for the second root we have to put b3 plus b4 n r1 minus ir2 raised to the power n. So this is our the solution if we have the imaginary roots are repeated twice, and we these b1 b2 bk b4 we have these are the constants, and we can find the values of these constants by using the initial conditions. So let's take an example. For this we have this recurrence relation an plus 4 plus 8 plus 2 plus 16 n is equal to 0. So what is this type of relation? This is our the homogeneous recurrence relation. So what is the first step? First step, you have to do an is equal to r raised to the power n, you have to put here. So when you put here an is equal to r raised to the power n, so which type of equation you will get? You will get r raised to the power n plus 4 plus 8 a raised to the power n plus 2 plus 16 r raised to the power n is equal to 0. Now, what you do the next step? Here, what is the less term here? We have r raised to the power n is the lesser term. So we have to divide by r raised to the power n this equation. In the last questions, we have the recurrence relation in terms of n minus 1 and minus 2. So our equation after putting an is equal to r raised to the power n, we divide by lesser term, that's r n minus 2. But here we have the lesser term is r raised to the power n, so we divide this equation by r raised to the power n. So we get here our characteristic equation, that is r raised to the power 4 plus 8r square plus 16 is equal to 0. So we get this fourth order characteristic equation. So how many roots of this equation? Because this is the 4-degree equation, so we have the 4 roots of this equation. So when you solve it, how to solve it? It is become r square plus 4 whole square, and so we have r square plus 4 and r square plus 4 is equal to 0. So what's the roots of this? These roots are plus minus 2i from this, plus minus 2i from this. So we have the 4 roots are here, 2i, minus 2i, plus 2i and minus 2i. So now we have the 4 roots, and here we see that these 2 roots are repeated twice. So what was the solution? The solution of this is an is equal to, we can write in this form, b1 plus n b2 2i raised to the power n, plus, because minus 2i again repeated, so this is b3 plus n b4 minus 2i raised to the power n. So like that you have to write your solution if you have the roots of the equation, the imaginary roots, and repeat it twice, and some other roots you have, so you can write in the form of like last theorems. So all these, I think all these types of roots I discussed here. So if you have these types of roots, so you can find the solution and in terms of this. So this is the required solution of this given recurrence relation. So this was the our homogeneous solution. In the next lecture we will discuss about the particular solution. So when we find the particular solution, so after combining this we get the final solution of the given recurrence relation. So now today's lecture is completed now. Thank you. Be happy, be healthy.